Hi, and welcome to my channel TechneMoira. Today's episode is about repairing my old power supply, the Hulk APS 3005D. So grab your favorite snack or drink, sit back and enjoy. So I bought this power supply I'd say about 12 years ago, around the time I started my channel, in fact. And recently, let's say the last year or so, the fault it developed was that I could never get the output voltage higher than around about 13-14 volts, right? So while this power supply is actually rated to go to 30 volts 2 amps of current, right? So, and in fact it goes even a little higher than 30 volts. I can turn it up all the way up to 32.5 volts, right? So the other thing that was bugging me about this power supply is that it was really loud. I mean, there is a fan inside to cool all the parts inside, right? The transformer, the voltage regulators, etc. But the way it was built originally was that as soon as you switched on the power supply, the fan would start to blow full tilt, which was really loud, and after a while can be really annoying and tiring, especially if you have to work on equipment and you need to listen for the tiniest sound coming from it. I mean, I'm thinking like, for example, repairing radios and stuff like that, where sometimes there are only very tiny little sounds you can use to diagnose a fault, right? So I set out to repair this lab supply and to upgrade it with a fan speed control, one that I designed myself. So yes, I succeeded, as you can tell. It's pretty accurate now. I tried to calibrate it as well as I could, but yeah, it's running well now and it's absolutely quiet. I'm sure none of you can tell that the fan is actually blowing right now. There is this one thing though that really annoyed me about this power supply. That is that I went to look for a schematic of this power supply, and in fact I found one, a schematic, because apparently these power supplies are pretty generic. You can find them by the thousands on the internet. Yeah, so I did find a schematic which, let's say, approximates rather closely what's inside, but it isn't identical. And that really forced me to go the whole mile and to actually do some reverse engineering to try to figure out which parts were not on the schematic and how they functioned, which in the end would turn out to be crucial to find the fault, which made it run badly. So there you go. Enough talking, let's jump right in. You can find them at a reasonable price, I'd say around $70, or on Amazon or eBay. And this one is one that can deliver up to 2 amps, 30 volts DC. It also has a negative supply line as well, or rail if you prefer, and you can set the current. It has a coarse and a fine setting, and you can set the voltage. Now, I've had this power supply for, I'd say maybe 10 years now, and it served me well till not too long ago, when it started to develop a very strange fault. And the fault would be that I would set a certain output voltage. Okay, so I would set an output voltage at, let's say 15 volts. Yeah, like that. And the voltage would drop, you know, without load or anything attached to it. So for some mysterious reason, the power supply just can't maintain the selected voltage. There you go, 10 screws. Let me disconnect it from the AC. Okay, so there. So there you go. There's not much inside my power supply except, well, a huge lump of a transformer, which is this thing here, and boy oh boy is that a big transformer. I mean, it's supposed to be able to supply 2 amps, right? So no wonder it's as big as this. Let's see. The other things you can see inside is the fan that blows some cool air into the power supply, and the regulating transistors. You see them here, yeah, on a heatsink, which is cooled directly via the fan. And then you see some high power or high current rectifier bridges. There are, if I'm not mistaken, 2 maybe, or maybe just 1. Let's see. Okay, so by the way, this is the back of the power supply. So let me see. No, okay, there's only 1 bridge rectifier. Okay, so there's a bridge rectifier down there, and then there is the instrumentation panel, right? So you could say the power supply proper, which is just a small main print board here and a display print board up there. Alright, so What I'm going to do is I'm going to unmount the front of the power supply so that I can work on it a little bit more easily, you know, because I can't reach or measure anything on the main PCB of the power supply in its actual position. So I need to release this from the case, and I might even have to release the heatsink for the power transistors to be able to work on that as well. Alright, I am nearly done disassembling the power supply. So as you can tell, I disconnected or disassembled the heatsink for the power transistors which do the power regulation. I also unmounted the fan, and as you can tell, I also unmounted the front panel, but I need to unmount the potentiometers for the current and the voltage setting. Yeah, and I'm not using any special tool for that. I'm using a flat nose or duckbill plier, you know, to grip the nut that holds in the potentiometer. And I need to do all four of them because the main PCB is held to the front panel with the potentiometers, right? So here you go. See? So I need to undo four of these nuts. Okay? And it's easy enough with the duckbill plier and a little bit of patience. Alright, this is a close look at the main PCB of the power supply, and at first glance I do not see any faulty components. I mean, like burnt components or broken components, or even leaky ones, like, you know, the electrolytic capacitors, for example. Yeah, it all looks pretty normal to me. So now I should say that I do have a schematic, but the schematic is not 100% the same circuit as the one you're seeing or looking at right now. Okay, but it can serve as a sort of a guideline, I suppose. So I think to repair this I will have to use common sense and some logical deduction, you know. Helped, of course, a bit by the schematic I have, but yeah, I'll have to reason this one out. Especially so since there is no obvious problem that I can detect on this main PCB. By the way, I did disconnect the display, the readout, okay, so which is mounted on a separate PCB, okay, and this basically has only two connections. One that goes to the transformer from which it gets its power. So the display is actually powered via a separate little power supply. Okay, so you can see the rectifier bridge over there, and then right next to it I suspect is the power regulator, but there is no label on the power regulator. Now there's one thing I do need to warn you, that is that the chassis, so the box or the case into which the power supply is mounted, is made totally out of metal, okay, for, I suspect, shielding purposes mainly, but it also means that it is connected to the common ground of the power supply, and more specifically the output of the power supply, right there, right, the center tap. So be careful when you work on the main PCB while it is unmounted from the front panel. Yeah. You know, don't make any short circuit between any traces on the main PCB and the chassis, the actual chassis of the power supply, okay? Or you'll draw a huge spark if the main filter capacitor is still full of voltage. Alright? I found a schematic which is closer to the circuit of my power supply, which is, although quite generic, it seems there are many versions made of this power supply, and well, as I said, this schematic here is much closer to reality, right? Now I'm still trying to trace what could be possibly the problem, right, in my power supply, and after studying the schematic for a while, I discovered basically two large parts, you could say, in the circuit. The first would be this one here, the lower part here, which is attached to this transformer here, and that would be, you could say, the main power supply. Alright, so that provides for the output voltage of my lab supply. But then there's a smaller power supply here, yeah, which has its own windings on the transformer, and that provides the power for a number of circuits. Namely, it provides the power to the fan, it provides the power to the safety relays over there. These relays activate when there's a short, or if the lab supply might overheat, okay? And apparently this power supply here also provides the power for the LM324 quad op amp, which regulates the voltage that you want to set with the potentiometers on the front panel, right? So the 4 op amps in the LM324 get their power, at least the top two ones for sure get the power, or their power, from the separate little power supply over there. Now I'm still trying to discover the origin of the fault which causes the dropping output voltage of the lab supply, right? Now, if this little power supply here at the top doesn't function normally and doesn't give out a stable voltage to the regulatory or the regulating op-amps, then no way can you expect the op-amps to regulate the power correctly, right? So what I'm going to do next is I'm going to investigate this little power supply on the main PCB, and in fact it is located right down there, and you can see one of my measurement probes attached to it right there, and more precisely is attached to the output of the 7812 power regulator. Okay, so you can see the rectifier bridge, which is over there. Alright, and the connector right next to it is the power input, on the left I mean, the yellow, black, yellow, that's the power input. The connector to the right of it, the red and the black, goes to the fan. Okay, so that little fan over there. Now the power to the fan is unregulated. Okay, the fan doesn't need regulated power, but the rest of the circuitry, and you can see the LM324 down there, alright, does need a very stable voltage. Now, as I said, the 7812 voltage regulator, which is this transistor here with its own little heatsink, alright, must provide for an output voltage which is very stable and which should be very close or totally equal to 12 volts, alright, because it's a 7812. So this is the voltage I measure at the output of the voltage regulator, 19.54 volts, so 19.5 volts, which is obviously not correct at all, right? So yeah, there is a problem there. While I'm waiting for the replacement parts for my power supply, I decided I would make a small temperature controlled speed control for my fan, or more specifically the fan that cools down my lab supply, so that fan over there. Now if you look closely at the label, it's not quite clear whether they mean the fan is a 24 volts 18 amps fan, or it needs 24 volts 0.18 amps. Now I tend to believe that it's probably the latter, yeah, so I think the fan probably consumes about 180 milliamps. Now funny thing is, when I look up the specs of this fan on the internet, the current it uses that I generally find on the internet is about 90, so 90 milliamps, yeah, not 180. So yeah, I thought to do my further calculations I took a happy medium of around 150 milliamps. Yeah. So if some of you know exactly how much this fan draws, I mean in current, then please let me know. I'm curious whether it's either 90 milliamps or the 180 milliamps. Alright, so I'm going to build the speed regulator on a little breadboard like this, you know, and once it's done I'll show you the finished build. Don't worry, I'll also show you a schematic of the speed regulator. Now some of you might think, okay, but why would you want a speed regulator for the fan at all? Well, when I switch on the lab power supply, quite often I need only very small currents and low voltages, which do not heat up the power transistors for that regulate the voltage. So the fan still blows full tilt even when it's not necessary, and that makes a lot of noise. So I prefer the fan to run slowly and silently when the lab supply is rather cool, but of course I want it to run faster if the lab supply starts to run hot, right? So that's the reason I want a quieter lab supply. Alright, for those of you who are interested in building a fan speed control for yourselves, this is the schematic basically of the speed control. Okay, it's built around an LM317 voltage regulator, which can draw about 1.5 amps, or source if you wish, 1.5 amps at maximum 35 volts, yeah, which is perfect for the application we're using it for. Okay, so at the left here you see a 1 kilo ohm quarter watt resistor with its one end connected to ground and its other end connected to the outer pin of a 50k trimmer, 50 kilo ohm trimmer. Okay, the wiper of the trimmer is connected to the left pin of the LM317, which by the way is commonly known as designated with the letter A. Can't remember right now what the letter, yes, adjust. Okay, so adjust, output, input. Okay, so it's a bit peculiar the way the pins are assigned to the LM317, but that's how they build it. Okay, so there you go. So a 1 kilo ohm to ground and the other end to one end of the trimmer, the wiper of the trimmer to the adjust pin of the LM317. Then you need to connect a 270 ohm quarter watt resistor with its one end to the output pin of the LM317, and then its other pin to one of the leads of the NTC resistor. I mounted the NTC, by the way, on some leads, you know, long enough so that I can place it right next or right on, in fact, the heatsink of the power transistors. And I used a small eyelet to mount the NTC. You can in fact see the NTC down there. It's a tiny little transistor in the shape of a drop, yeah, and I surrounded it with a little bit of heat conductive paste, yeah, and I gently clamped it into this eyelet here, you know, which is just a 2 cents eyelet you can buy anywhere. Okay, so yeah, that's the NTC. So again, so you connect a 270 ohms quarter watt resistor with its one lead to the output of the LM317. The other lead goes into one lead of the NTC, and the other lead of the NTC goes to the adjust pin of the LM317. Right? Then the input voltage for the fan, which can be, you know, anywhere between, say, 6 volts and 24 volts DC, yeah, it just happens to be 24 volts in my lab power supply, comes into the input pin of the LM317. Okay, so the output pin is then connected to the plus of the fan, yeah, and the negative of the fan is connected to ground. I put a capacitor over both pins, yeah, of 100 microfarad, 50 volts. If you wish, you can delete it if you don't want to spend the money, but I did it because I wanted to suppress any sort of noise that the fan would generate. Okay, it doesn't have to be necessarily 100 microfarad. I mean, a 47 microfarad or even a 20 microfarad would do as well. But I would advise you to take one which can hold up to 50 volts, okay? Just to be on the safe side. Alright, I finished the speed regulation module for the fan. Alright. And it's built around a voltage regulator, namely an LM317. Alright. I put it on a small heatsink because at full tilt there will be quite a bit of current running through the whole thing, and more than likely it will have this to dissipate, I'd say around 2.5 watts of power, right? So that is when the fan will be running at full speed. Okay, so yeah, there you go. I unsoldered the whole plug to the fan from the main board over there. Alright, so, and in its stead I will mount the whole PCB you see here vertically. So namely, it'll be mounted like this, in the spot where the connector for the fan originally was mounted. Okay, so it'll be soldered down via these two pins here. Now the NTC I mounted in an eyelet, as you can tell. Alright, and there's a tiny little bit of heat conductive paste around the NTC. And the eyelet itself will be mounted on the heatsink of the power transistors. This is really hard to solder because there's really very little space to work with. Plus, of course, there is the added problem that the voltage regulator is mounted on a heatsink, right? So the heat I'm trying to apply to the contacts to be soldered is immediately leached off into the heatsink, right, which complicates a little bit the soldering of the whole thing, but eventually, of course, it does heat up and it does allow me to solder it. Okay, so let me see, let me give it a check whether I have no false contacts or anything, and indeed not. I don't think I have. So just to be on the safe side, let's measure if there is no short circuit there. Let's see. Okay. Okay. So let's measure with the clamps like this. Alright. Let's see if there's a short circuit or not. No. Okay, let's see on the other side. No. No. So here's a bit of a mystery. As you know, I replaced the L7812 voltage regulator, right? That one over there. Because I, rightfully so, I believe, suspected it of being the source of all my troubles. And in fact, it's on the schematic, it's this one here. Come on. This one here. Okay. So I replaced this one here, and when I switched on the power supply to measure a few voltages on its output and on a number of its parts, I noticed that the voltage regulator, the 7812, was becoming really hot, which meant that it was pulling a lot of current, right? Or at least there was a lot of current running through it. So, logically speaking, of course, I suspected the capacitor here at its output, okay, which is a 220 microfarad capacitor, which is this one over there. Now this is already a replacement, okay, so I replaced the original capacitor with this one. And although that had a slight influence on the voltage on the output of the lab power supply, it didn't actually solve any problem. So I mean the voltage at the output is still too low, which makes me think that there must be a short of some sort down current, right? So there are several possibilities, obviously. There are these two parts here, which the TL431 is what they call a programmable Zener diode. That theoretically could be shorted. This capacitor here, the 47 microfarad capacitor, could be shorted, or there could be a short, there could be a short down the line here. So right here, in fact, all the way down here. Okay, so there could be a short here somewhere in this part of the circuitry, but I'm not sure. So I need to figure out which component could possibly be the culprit. So you'll remember a minute ago I said that I was suspicious of all the parts that were located downstream from the 7812 voltage regulator, right? Because it was running really hot. And I am still suspecting, by the way, a short downstream. Now, I did replace that capacitor here, which, by the way, is not a 47 microfarad, but a 470 microfarad. But unfortunately, that didn't change the situation. So I was measuring a few voltages all over the circuit, and I started touching, components with my pinky finger, with my pinky, just to, touch exactly the part that I wanted to investigate, let's say. And since this is low voltage, quote-unquote low current, I wasn't afraid of getting electrocuted. Obviously you shouldn't do that on a high voltage power supply or something like that, but either way I started touching the parts on the power supply, especially in this part of the circuitry, and my pinky landed on the TL431, and yeah, I nearly burned the tip of my pinky. It still hurts a bit. So this component here was like burning hot. So I am going to replace it, but that doesn't mean that I found the source of the problem, right? It's possible that if I replace this component, which is this little component here, that the problem will be fixed, yeah. So replacing this component might fix the problem, but there's no guarantee until I do fix it. Now I do have a replacement, and I'll show you the replacement right here. So, and the replacement is on the left. Okay. So obviously the replacement is not identical to the original one. I mean, the pins are definitely different, and it's slightly smaller than the original one, but only very slightly so. But yeah, I have every confidence that this part is a correct replacement for that one. Alright, so I replaced 4 broken parts on the main board of the power supply. A resistor, a 1 microfarad non-polarized ceramic capacitor, a S8050 NPN transistor, and a 18 volts Zener diode. Alright, now the placement of these parts is, when you look at the power supply board, the placement is basically the transistor is located right here, right next to the TL431 programmable Zener diode. Okay, so let me give you a close-up shot right there. Okay, so this power supply here, because there are actually 2 power supplies on this board, this power supply here supplies the LM324 op-amp, quad op-amp, and its ancillary parts with power. Okay, the S8050 NPN transistor is this one here, and this is the TL431 programmable Zener diode. So it would appear that the S8050 right here broke down, and it was basically acting as a resistor. Yeah, so it wasn't working as a transistor anymore. The result of that was that the Zener diode you see here, which is an 18 volts half a watt Zener diode, sort of, you could say, burnt up. Yeah, so it broke down in turn, because there was way too much current being drawn through it. Now, although I did replace initially these 2 parts here, there was absolutely no change, no noticeable change in the working of the power supply. So you remember that the power supply at its output delivered about half of the voltage it should normally deliver, so even less than half. Yeah, So normally this power supply is rated to deliver nominally 30 volts DC at about 5 amps, okay, and it was delivering at most 13.5 volts or so. Yeah, so like I said, so the symptom was that the power supply just couldn't deliver its maximum rated output voltage, or current for that matter. Now, as I said, this transistor here and the Zener diode had broken down, and I replaced them, but that didn't change anything. So obviously the fault had to be somewhere else, and it took me, yeah, it took me at least eight hours or so to figure it out, because basically what I ended up doing was sort of reverse engineer the power supply you see here, in an effort to try to understand what was going on, okay? Because when you compare this circuit with the schematic that I found online, there were some noticeable differences. Yeah, so the schematic I found online wasn't what you would call exactly accurate, okay? So yeah, I spent quite a few hours trying to figure out what was going on with this power supply. And believe it or not, the culprits in the end turned out to be this tiny little resistor down there. I'll show you. So the culprits turned out to be this resistor here and this 1 microfarad non-polarized ceramic capacitor, yeah, which is actually pretty rare, I would say, for a ceramic capacitor to break down, but apparently it did, and so did this resistor. None of the parts showed any traces of overheating or being broken or shorted or whatever. You know, if you look closely at those parts, you really can't tell that they are broken, right? So, and these two parts here I replaced on the print board. I'll show you. Those two parts are this one here, yeah, this capacitor here, and then the resistor above it, that one there, yeah. If I'm not mistaken, the resistor is a 1.2 kilo ohm quarter watt resistor that I used for replacing the broken 8 watt resistor that was there before. Okay, so yeah, those two parts were basically shorted internally, yeah, and go figure why. I don't know why. Don't ask me why. It like I said, it's not visible. Okay, if you look at the parts, you really see absolutely no trace of burn marks or breaks or whatever, yeah. So yeah, in the end, like I said, I figured it out, and actually I figured it out in the end by using cold spray on these two parts here, okay. So when you spray cold spray on parts like these, you basically refrigerate the part temporarily, which sort of resets its more or less its original value or thereabouts, yeah. And indeed, when I sprayed these two parts with cold spray, the output voltage of the power supply started rising substantially, yeah, which of course immediately told me that these two parts had to be broken. And that's exactly what I did. I replaced them with the parts you see now. So yes, indeed, I used again a ceramic 1 microfarad non-polarized capacitor and a metal film resistor to replace the two original parts. Now, since I was inside or working on the power supply, I thought to myself that I would at least replace a few capacitors, which I did. Yeah, I replaced basically these two here and these two there. Okay. So yeah, who would have guessed, that those two tiny parts right here, yeah, a capacitor and a resistor, would have caused all that trouble in a relatively simple power supply. I wouldn't say it's simple, but yeah, I mean, if you look at the schematic I found online of the power supply, now I have to tell you, this power supply, yeah, I mean, mine is branded Hulk APS 3005D, but these power supplies are like a dozen a dime on the internet. Okay, so this is really basically a very, very common power supply. You can find them anywhere and at let's say relatively cheap prices. Okay, so basically these power supplies are absolutely generic, yeah? And the schematic I found online, so the schematic is right here. Come on, focus, focus. There. Okay, so the schematic you see here, yeah, is the generic schematic I found online. Okay, so it's absolutely not identical to the circuit you see there. Okay, so this circuit here, okay, this circuit here is totally different. Well, is quite different from what you see here. Now you might say, okay, but then if they are so different, why did you use a generic schematic like this to help you yourself, right? Well, to have a schematic which is more or less approaching what the circuit in reality is still better than have no schematic at all. Okay, so I decided to use this schematic as, let's say, a guideline more, yeah, like sort of a temporary map of the circuit to help me along. And by and large, let's say for quite a few things, it's similar to the circuit, but it's not identical. Now, the parts that I replaced were this L7812 here, okay, Then I replaced, obviously, the electrolytics you see here. Yeah, the values are different on the schematic, so you need to go by the values of the parts you find on the circuit board itself. The Zener diode, the 18 volt Zener diode, is this one here. Now on the circuit it's marked as a 6.2 volts Zener diode. Mine was an 18 volt Zener diode, and it is marked as such on the circuit board, fortunately. Okay, so the transistor I replaced is basically this transistor right here at the bottom of the screen. Okay, so as you can tell, it's an NPN transistor. And then the resistor and the capacitor I replaced, yeah, are these two here. I'll show you. So the capacitor, the 1 microfarad capacitor, is right here. Okay, this one here. Yeah, it's marked as a polarized capacitor on the schematic, but basically it was non-polarized on mine. Okay, and the resistor I replaced is this one over here. This one over here. Okay, yeah. That one turned out to be a 1.2 kilo ohm 1/8 of a watt resistor. Okay, so yeah, I replaced that resistor and I replaced the 1 microfarad capacitor at the bottom, right there, right there. Okay, so the astute among you will immediately see there's something weird on the schematic. Yeah, so like I said, the heart of the power supply is an LM324 quad op-amp chip, right? Now on the schematic there are indeed 4 op-amps, but the main op-amp, so the one, this is the op-amp to regulate the current, yeah, supplied by the power supply, and it is marked as an LM741, not as 1/4 of an LM324. So yeah, that threw me off a little, but then I soon realized that a few of the components and connections you see on this schematic couldn't be right. Yeah, I mean, if I compared it with the original circuit, well, with the actual circuit, yeah, when compared with the actual circuit, these connections and parts couldn't be identical with the circuit. Okay, so what I quickly realized is that you can simply ignore that little cap connected to pin 5 of the LM741, so you could basically delete it. When you look at the op-amp, which is used to regulate the voltage output, you also see it's drawn around an LM741, and again you can safely delete anything connected to pin 5. Yeah, because that little cap and pin 5 was meant to be on an LM741, not on an op-amp, 1/4 of an op-amp of the 324, yeah, or I should say a quarter of the LM324, yeah. And obviously when you look at a schematic of the LM324, you'll notice that the inverting and non-inverting pins of, for example, this op-amp are located on pin 2 and 3, but that's pure coincidence. The output, however, of the op-amp is on pin 1 of the LM324. So yeah, it is very, very confusing. So that's why I had to, you could say basically I had to reverse engineer the whole thing, really, to try to make sense of what I was seeing. Okay. Also, you'll notice that the LED, which by the way is a green LED on my power supply, which signals that there is power on the output, yeah, is powered via a Zener diode right here and a resistor. Okay. I looked all over the circuit, all over, and I could not find either this Zener diode or this resistor. It appears that whomever built this power supply elected to replace these two parts with an NPN transistor and a few resistors around it to power the LED, yeah, and he moved the LED over to the circuit with the transistor. Okay, same thing for the current setting, yeah. There too you see an LED, and this is a red LED, yeah, and again a transistor and a few resistors were used to power the red LED rather than to power it in line with the output of this op-amp here, yeah, which is another of the 4 op-amps in the LM324. So yeah, major reverse engineering I had to do to try to make sense of it all. But okay, here you go. The power supply does function now. So hopefully now it will remain a reliable, useful power supply. One little detail, or maybe two, that I should mention to you is I mounted the replacement Zener diode. If you look at it closer, yeah, I used basically all or most of its leads, yeah, and I mounted it high up above the circuit board. Okay, the reason for that is that even with good working parts, this Zener diode still draws quite a bit of current and becomes uncomfortably hot. Okay, so to give it the chance to dissipate a bit more heat, I mounted it like this with its leads quite a bit longer and floating in free air instead of mounting it like the original was close to the circuit board. And indeed I think that will help a little, yeah, to cool it down. Also, although you can't see it, I did put some heat conductive paste on the back of the L7812. So there you see there, that was the original placement of the fans connector right there. Okay, so I unsoldered it from the main board and I soldered it on my print board here. Okay, right here. And that way I could keep the whole design clean. I also placed the components, as you can tell, not at one end or the other of the little circuit board, but somewhere in the middle, such that when I place it back, when I place the circuit board inside or on the main board of the power supply, it would fit nicely around all the other parts on the board, right? And that's what I'm going to do next. I'm going to mount the fan speed control on the main board, give it a quick test, and I'll show you the result. Alright, the power supply is on, yeah, but obviously there's no current being drawn through the power supply, so it isn't running hot. As you can tell, the fan is blowing slowly. I can still feel some current, air current, but it's not like, you know, like a hair dryer or something like that. It's really quiet and I feel a little bit of air current. And that's the speed at which I set the speed control with that little trimmer I showed you. Yeah? Now the NTC right here is what controls the speed of the fan, right? So let me show you what happens when I heat up the NTC a little bit with my soldering iron. Yeah, watch the fan. There you go. The NTC cools down and the fan slows down. Now, what I would recommend is that technically, if you wish, you could make the fan blow really slowly, like really slowly, and would generate absolutely no noise, but also it wouldn't generate much of an airflow inside the power supply. Yeah, so the components do need a little bit of cooling, so I would advise setting the fan at, let's say, a slow but steady pace like it is now. Yeah, I can feel a gentle air current, okay, right now. And if you want to know a value, well, I would say if you're pumping in around 6 volts DC or a little bit less into the fan, you'll get more or less the speed, the initial speed, or the speed at rest that you desire. Yeah, but then again, I leave it up to you. Like I said, by turning the little trimmer on the speed control, you can set the speed of the fan at quiescent state and when you're drawing a lot of current. And there you are. Everything is mounted back. and tested, and you can see the main board of the power supply down there, and then the front panel display PCB mounted in the front, and then the new added speed control PCB over there. Alright, so by the way, I mounted the temperature sensor for the fan speed control over there. Okay, so there it is, and the power transistors are underneath, of course. Alright, so yeah, I dressed the lead on this side as well, and in fact I dressed them in such a way that they could lay flat against the transformer. They are too short to lead them over the transformer, but they are long enough to go alongside it. And the way, or the reason rather, why I had to dress the leads this way is because the space between the case that sits around the power supply and the transformer is very, very narrow. So dressed like this, the leads will fit perfectly. But had I bunched them together with just one zip tie, then that would have been too wide to close the case neatly. Okay, so yeah, and there you have a view of the main PCB, but from the other side, and there you can see the fan speed control PCB that I built. Alright, yeah, it's a nice little power supply. Sure, it's not probably the best quality power supply one can have on the market, but you know, I'm a bit strapped for cash, and well, truth be told, I'm a pensioner. I don't have that much money left to spend on new material, so I have to make do with what I can afford. So there you go. I hope you enjoyed this episode. Give me a thumbs up. Please subscribe if you feel like it. And I'll see you all back for a new episode on my channel. Thanks for watching.